So hello everyone. Today we are going to start our numerical linear algebra, and we will start with roots of nonlinear equation. So we have many techniques, we have many methods from which we can find the approximate root of a nonlinear equation. So we are going to start with bisection method today, and we will see uh, all the concepts and the techniques, how to implement the techniques, and everything about the bisection method. So let's start. So first of all, we can see that we have different kind of equations uh, for which we can find the roots, right? So uh, the very simple type of equations are polynomial equations, and the complex one are the transcendental equations. So we can find the roots of both of these types of equation by using the bisection method technique, but it has a condition, and the condition is f of a times f of b should be less than 0 in any interval. Okay, that kind of interval, that kind of 2 points should exist where f of a times f of b should be less than 0. Okay, that is negative. So let's see the bisection method. This method is based on intermediate value theorem. So IVT theorem we have, and it is based on this theorem. So we will see first the IVT theorem, that is intermediate value theorem. And first of all, let's understand intermediate value theorem, and then we will be able to understand bisection method, because in each step of bisection method we use intermediate value theorem. Okay, so let's see the concept behind the intermediate value theorem. So first of all, let's read this out. Suppose fx is a continuous function defined on the interval a comma b, fixed interval, closed interval, with fa and fb are of opposite sign, that is fa times fb should be less than 0. So this is the condition. If this kind of condition is met, okay, so if we find this kind of 2 points where f of a times f of v, that functional value, the multiplication of functional value in those 2 points is less than 0, that is negative, then in that closed interval there must be a single root at least. Okay, at least there must be one root, or it can be in odd numbers. Okay, so then there exists at least one or odd number of roots in that interval, closed interval a comma b. So that is the main concept, and I will try to show that by using a little graph here. Okay, so let me draw a little graph so that so this is a function fx, let's say. Okay, so we need to find first of all 2 points. Okay, 2 points such that f of a times f of b should be less than 0. Okay, that is the multiplication of two functional values. Okay, functional value is at those 2 points should be negative. So that is the thing we need to find. So we will check to find these two points, right? To find these 2 points we need to check for every point, right? So we will check from 0, and we can find either positive or negative at that point, right? So we can find the functional value either positive or negative at the point 0. So if we find positive, then we need to look up for the negative value. So for which point we find the negative, so we can just increase the value, and like we can put 1 2 3 4 like that, and we can just test that at which value that the functional value is negative, right? So we just have to find that value, and whenever we find that value we can just conclude that there is at least one root between those two points, right? So how can we say that thing? So we are going to see that thing. Okay, so let's say that this is point a and this is point b. Okay, so these are 2 points, and you can see that this at this point A here the functional value is positive, right? Here the functional value is positive, and here you can see the functional value is negative. Okay, so this value is the functional value. This is negative at point B and positive at point A. You can see that thing. So if that kind of situation occurs, then obviously between the interval of point A B, the graph, the if the function is continuous, then the graph should cross the x-axis for sure. You can see at this point the graph is crossing the x-axis. So if it is intersecting the x-axis, then that point of intersection is known as the actual root of the function. Okay, so we have function fx, and what is actually the root? The root is any value of a function. Let's say we have function of x fx. So if there is any value of x such that whenever we put into that function, that is fx function, it gives the result 0. Okay, it satisfies the equation. So in that case we say that whatever value we have put such that it satisfied the condition of fx equal to 0, then we say that value is the root of that equation. Okay, that function. So when does the value satisfy that kind of condition, that kind of function? That is when it crosses at that point which crosses the x-axis. Okay, so whenever a function at which whichever it is the point, okay, that point at which the function crosses the x-axis, that point is the root of that function. So that is the basic concept we need to know, right? So talking about IVT theorem, that is intermediate value theorem, it says that whenever we find 2 points, find 2 points, that is A and B, such that the multiplication of the functional value at those points is less than 0, that is negative, then we can say that between those 2 points at least one root exists. Okay, so what is the meaning of at least one? So I want to clear that thing as well. Let's say that we have this kind of graph. Okay, so we take A point as this one and B point as this one, let's say. Then you can see that the graph, how many times the graph is crossing the x-axis? 1, 2, 3. So you can see 3 times it is crossing the x-axis. That means all this value of x, right? All this value of x at which the function, the graph is crossing the x-axis, at which the curve is crossing the x-axis, all those points of x, all those values of x are the roots of the function, of that function. Okay, so that is the concept. You can see here there are 3 roots, right? The odd number of roots. So whenever we find two such points on the x-axis, okay, on the x-axis, we are just talking about the function of x only this time. Okay, so we are taking x-axis. So whenever we find such values of x, such points, wherever the functional value, wherever the multiplication of the functional values of those points, that is fa times fb is less than 0, that is negative, then we say that between that interval a and b, okay, between that closed interval a b, there exists at least one root. Okay, so that is the main theorem, IVT theorem. Okay, so now let's see that you can see the same thing is explained here as well. Let's move on. And what if we have fa times fb is greater than 0? So in this condition, you can see in this condition this condition actually doesn't satisfy the IVT theorem, right? So for the IVT condition, the condition for IVT theorem is the multiplication of two functional values at some points should be what? Less than 0. Okay, so if that condition occurs, then we can say that there are odd number of roots present in that interval. So but you can see that fa times fv is greater than 0. That means you can see both the functional value at a and b are positive. So you can see there are two roots actually, and there can be 0 roots as well. Okay, 0 to 4, that is even number of roots. So if there are 0 roots, then we cannot say that there is at least one root and use that interval to find the root. So we cannot do that. So there is always a possibility that there is a 0 root between that interval. So we don't consider this condition as a valid condition to find the root. Okay, so that is why we always consider fa times fa is less than 0 as a valid condition to find the root in that interval. Okay, so this could be even a valid in interval, but the thing is it can be 0 roots as well. For example, I have here one example, I think. So you can see in this condition fa and fb are both are positive, you can see. So in this condition there is no root, right? There is no root for this. So this condition can be there. So that is why we always find two such points such that fa times fb should be less than 0. So that is the intermediate value theorem. So I think I am very clear on this. So let's move on to the bisection method. So how do we use this intermediate value theorem in the bisection method? Let's see that thing. So it is the simplest iterative method for finding the root of the equation fx equal to 0. So it is based on repetitive application of IVT. For applying the method, we need two initial guess. So we need to guess a and b first. Okay, so we need that points, right? So we need a and b points such that at least we can say that the root lies between these intervals. So we need to have that interval first. Okay, so whenever we are finding a root of equation of any equation, then we need to first have an interval, at least an interval, so that we can say that the root lies between that interval. So we need to find that thing first. So to find that thing, we need to use the intermediate value theorem, right? So we will check for different values of x and find the functional value for different values of x. Okay, so we will put x equal to 0 in the function, we will put x equal to 1 2 3 4 like this, right? So whenever we get two different signs, whenever we get the condition fa times fb is less than 0, then we will take that interval as our interval to solve the question. Okay, so let's see how do we find the interval. So fx equal to 0, we have a function, and compute midpoint of a comma b such that, okay, so let's see. So I would like to explain a little bit about the bisection method here. So how do we use bisection method? So let me draw the similar graph as I drew before. So let me take this point as this is a, let's say, and this is b. So we have already found a and b using IVT by checking different points of x, right? So now we have found the 2 points, so that we can say that root lies between these 2 points, right, in that interval. So this a to b is an interval. Okay, so now what are we going to do is we are going to bisect this interval. Okay, so we are going to find midpoint of this interval, and then we are going to change the interval. We are going to bisect the interval, change the interval, bisect the interval, change the interval. So only 2 steps we are going to repeat again and again, that is bisect the interval and change the interval. So we need to remember only 2 things that we do in bisection method. The concept lies within the name of the method, that is bisection. That means we are bisecting the interval and changing the interval. So that is the only thing we should remember. Okay, so let's say that we are going to bisect this interval. So let's say that this is the midpoint, as almost, so let's say this C is the midpoint of the interval a b, right? So we have interval a b, so that the root lies within this interval, and we are going to bisect. We bisected the interval a b so that C is the midpoint of a b. Okay, so this C is the interval of AV, and now we are going to again apply what? We are going to find f of C. Oh, why is this coming? Come on, bro, don't come. F of C. So we need to find this value. Okay, so you can see here that we computed what? We computed the middle point. So we calculated the middle point, and now we are finding the functional value at that middle point. Okay, so and now we are finding the functional value of middle point, and when we get the functional value of this middle point, we already have the functional value of B, right? We already have functional value of A. Now we are going to compare between the functional value of f of C, f of A, and f of B. So we are going to compare these three things, that is f of A, f of B, and f of C. So either A or B will be replaced by this C. Okay, so we are going to decrease our interval. Okay, we are going to make our interval small and small in each iteration, in each repetition. Okay, so that we at last we can be very close to the actual root. Okay, so this is our actual root, that is we do not denote it with alpha, and we are going to get very close to this actual root. Okay, so the condition is given in the question. We will see that thing as well. So the basic thing is we bisected the interval, and now we are going to compare f of A, f of B, and f of C. So now we will again take what? First of all, we will compare f of A and f of C. Okay, so we are going to compare f of A and f of C. So if you see that f of A is this and f of C is this, so you can see both of the values are positive. That means we the root doesn't lie between this interval, right? We can say by using IVT, we can say that the IVT, the condition is not satisfied. Oh my god. Drink the water, bro. So the condition is not satisfied, so we can say that the root doesn't lie between, we can be sure that root lies between this interval, so we don't take this condition. So now we will check what? F of B and f of C. So if we check f of B, this is f of B and this is f of C. So you can see f of C is positive while f of B is negative. So f of B times f of C is negative. That means the condition of intermediate value theorem is satisfied, and now we can apply now we can say that there is at least one root between this interval. For sure we can say that by using IVT, right? So we take, now in the next iteration we are going to replace this A with C and B with B. So we are not going to replace B, but we will replace A with C. Okay, so so the left hand side is replaced, right? So we had the interval at first we had this size of interval, right? So whenever we replaced when we replace the A with C, then we will get only this interval. You can see in only one iteration, in only one repetition, we how much we have decreased the interval. So if we do this very large number of times, then the interval goes on decreasing very much. Let's say that the midpoint of these two would be here, and we can take this interval, and then midpoint would be here, and we can take this interval. So likewise interval here and this interval. So in this way the interval decreases so very fast, right? So the interval decreases and it will approximate to the exact value of the root. so it will approximate to very close of the root, so that we can say that we have found the root of the equation, right? So let's see now the actual question solving technique. So this is the general form of representing the steps. You can see that here oh, okay, so you can see that here we are finding the midpoint, right? So first of all, the interval is this, and we are finding C1 midpoint, and we are checking if AC and CB. So I have told that is we are checking between A and C and B and C, right? So so whichever satisfied the intermediate value theorem, then we will replace C with that one, okay, so that we are able to decrease the interval. So let's assume that this satisfied the condition. So that means we will be taking A1 as A and B1 as C. So so that is the condition. So B is replaced with C, you can see. So that is the thing. So we will do this for many iterations, for many repetitions, and at the end we will find the actual root. So when we will be able to find the actual root, that we will see now. So before that, let's see that at what rate the interval is decreasing, and what is the order of convergence basically. So so you can see the length of I1 is equal to B1 minus A1, that is B minus A by 2. So the points that we had just found at the beginning, at the very beginning, that was A and B, right? So the first interval was A and B, right? So the first interval was A and B, and after bisecting it once, the interval becomes half, right? So you can see here like this. So this is A and this is B. Whenever I bisect this and denote it with C, then this interval becomes only this, right? So you can see in each iteration the interval becomes half, right? So in each iteration the length of interval becomes half, and you can see this is the interval, length of interval in one iteration only. So if we do n number of iterations, if we repeat the same thing n number of times, then we will get, okay, if we repeat this n number of times, so if we repeat this n number of times, then we will get we can represent the interval length with this formula. You can see B minus A divided by 2 to the power n, right? So first of all it will be half, and the half, and then again half, so something like that. So we can represent it like this way. So let me just give you some, okay, so pictorial representation. So this is A, let's say, this is B, this would be our C, and then this would be our, so this is the first interval, that is initial interval I0, and this is then this is our I1, and then again I am bisecting, and here is another C, let's say this is C1 and this is C2, then this would be my I2, okay, this would be my I2, okay. So you can see that this I1 is actually I0 by 2, right? It is half of the first interval. You can see this interval is just double of this interval, that means this I1 is half of I0. And if you look over the I2, then I2 is 4 times less than I1, sorry, I0, okay. So in this way it is in the 2 to the power n order of decrement, you can see, that means divided by 2 to the power n. So that is the thing here we need to understand. And then let's see. So the rate of convergence, you can see here the rate of convergence is 1 by 2 to the power n. Okay, so what is the rate of convergence? It is we can understand it like at what rate it is our root is moving towards the actual root. Okay, at what rate the midpoint is moving towards the actual root. Okay, so that is our what, that is our rate of convergence. We can understand it like that. And then when to stop. So let's see when to stop. So in question we will be given tolerance value. So we denote it with epsilon. You can see like this, epsilon. This is known as tolerance value. So whenever we get tolerance value as the given value in the question, so in that condition we stop the iterations. Okay, in that condition we stop the iteration, and whichever midpoint we have got at the last iteration, that will be the approximate root of our equation. Okay, so what will be the condition then? So that this is the value. So how to find this value? So let's see that now. So stopping criteria, we have 3 criteria, but out of these 3 criteria, we say that second is the best. The second criteria is the best, but we when finding the solution we use this formula, Cn minus 1, that is mode of this value. Okay, so we use this as our to find the difference between the roots, or we can say the approximation, how much correct is that approximation. Whenever this value is less than tolerance, then we stop our iteration, right? We stop our calculation and we say the midpoint is the approximate root of the equation. So that is the thing. So what is Cn and what is Cn minus 1? C1 means the midpoint. Okay, so C1 is the midpoint and Cn minus 1 is also the midpoint. That is the previous iteration, for previous iteration and next iteration. That is the thing. So we will see now this in the question. So let's see the question. That here you can see Cn minus 1. What is this? So we will make this kind of table. I don't think this is required or this is required. We can just see that we need to use FB and FA instead of this. So the thing is, we will make table of A, B, C and FA, FB and FC. Sorry, so I did a mistake. That is, here should be FB. So instead of this we will use FB. So FA, FB and FC we will use this, and then we will compare. Okay, then we will compare between FC and FA and then FC and FB. So whichever gives the value negative, we will use that interval as in our A and Bn. Okay, A and Bn. So now what is Cn and Cn minus 1? Let's see that thing. So we are getting the midpoint here. You can see this C1 is this one and Cn minus 1 is this one. Okay, so the midpoint of the current iteration and then the previous iteration, so that is this value. So whenever this value is less than this tolerance, then we will stop our calculation there, and then we will declare, or we can say that this Cn value is the approximate root. You can see this value is the root of the equation fx equal to 0. So that is the way of calculation. And so what is remaining now? So number of iteration of bisection method. So to calculate the number of iteration, we have one formula, and we will see derivation of that formula as well. So now we can directly see, by seeing the interval, when we have the interval in which the root lies. So when we have that thing, and when we have the tolerance value, then we can directly say that how many intervals are required to approximate the root about that tolerance value, right? So for that, let me just explain something. So I'm using the same same graph. This is A, this is B, and this is C, let's say. Okay, so so main thing we need to remember here is and this is alpha. Okay, this is the actual root. So you can see this is our first interval, I0, and this is our second interval, I1. So if you see here that you will be able to see that I1 from here to here. Okay, so this is I1 actually. So it is not so clear, but still let's just adjust. Okay, so this is I0 and this is I1. So we can write like I1 as I0 divided by 2, and then I1 is actually B minus A. Sorry, not I1, it is I0. I0 is B minus A divided by 2. So in that way we can just write that IN is B B minus A divided by 2 to the power n, right? So we can write this kind of thing, right? So yes, we can write this. So if you see the thing, you will be able to see that I want to compare this thing. I want to compare this thing with C minus alpha. So you can see that I1 is greater than C minus alpha here. So in this figure or graph, you can see that C minus alpha is less than the I1, right? C minus alpha is less than IN. So I can write this. That C minus alpha is less than or equal to B minus A divided by 2 to the power n. So I can write this, right? So while approximating, I am given the tolerance value. So this length of interval should be what? This length of interval should be less than the tolerance value. So we will write that so this value should be less than the tolerance value, right? So from this we can see that we can write this, and or this is the OR condition. We don't need this one. We can write this thing from here, you can see. Okay, so the thing is we need this kind of condition. And now from this we can just derive the formula for n. So if I take so if I take log on the both sides, and if I try to calculate the expression for n, then I will find this kind of expression. So this is the value of n, that is how many number of iteration do I need to do to calculate the root of an equation by using the bisection method. Okay, so the main thing we need to remember is, whenever we find this kind of values by using this formula, whenever we find this kind of values like 6.1 or 6.4, so in this condition we need to use what we need to use ceil function. Okay, we need to use ceil function, that is we will round up to the upper value, that is we will write it as 7, right? If we found 6.4, then we will use ceil function and write, and we will round up to higher value. Okay, so if we found the point, then we will round up to the higher value. So that is the thing. And you can see here is the one question, and you can see this is the equation, and we are given interval and then this tolerance value as well. So that means we can easily say how many calculations, how many iterations are required to find the approximate root of this tolerance of this equation. So we can directly use that formula to do this. Okay, so that is the condition. And then here are some examples. Now let's see the drawbacks of bisection method. So main drawback of bisection method is that it is slow, right? The method is slow because it divides it only into half, and this is a very low order of convergence, and we have much more better methods than this one. So so that's why we are saying this is slow, right? So it is like comparative. And the second point is fx equal to x square touches the x-axis, then IVT cannot apply. So the thing is, IVT we cannot apply whenever there is no negative functional value, right? So you can see this graph, there is no negative functional value, right? So the functional value is always positive on the, it is always on the positive y-axis. So we cannot apply IVT in this case. So in this case we cannot apply IVT, that means we cannot use bisection method. So the method fails here in this type of equations, right? So we know that the x equal to 0 is the root, but still we cannot directly find by using the bisection method in this kind of equations, right? So that is one drawback we can say. And then you can see in this kind of fx equal to 1 by x, this is a rectangular hyperbola, and in this kind of equations fx is not continuous at x equal to 0, and IVT is not applicable. So in this kind of equation as well, we cannot directly apply IVT, right? Because it is not continuous at x equal to 0. But still IVT, if we just see the condition of IVT, then you can see this kind of condition we can make, we can derive this kind of condition, but still it is not applicable, okay, because it is not continuous function at x equal to 0. So that is the thing. And in these three conditions we can say that in two conditions the bisection method fails, and we saw the three drawbacks of bisection method. And in the next video we will see the Newton's method or maybe fixed point method. So we will see all the methods. That is it.